Saturn is one of the most beautiful planets in our solar system, with its giant rings shining in space. This giant planet is so big that more than 700 planet Earths could fit inside it. As you relax and get ready to sleep, we are going to explore 100 incredible facts about this fascinating world that sits more than 1 billion kilometers away. Its mysterious rings are made of billions of pieces of ice, some as small as grains of sand and others as big as mountains. But here is something that will surprise you. Saturn is so light that it would float in water if you found an ocean big enough. How can something so giant be so light? As we travel through these cosmic wonders, you will discover secrets about this planet that has more than 80 moons spinning around it. Get ready for a calm journey through space, where each fact is a small star of knowledge lighting up the vastness of the universe. Subscribe to the channel, leave your like and comment what part of the world you are watching from. Get comfortable and relax. Let's begin. Tonight, we turn our attention away from Earth and towards something far more distant, something that has captured human imagination for thousands of years with its silent beauty. We are going to travel together across more than 1 billion kilometers of empty space to visit Saturn, the jewel of our solar system, the crowned giant that floats in the darkness beyond Mars and Jupiter. As you settle into comfort and let your breathing slow, we will explore 100 remarkable facts about this extraordinary world, each one a small window into the cosmic wonder that surrounds us. Saturn waits out there right now as you listen to these words, spinning slowly in the cold darkness, its rings catching the distant light of the sun and scattering it into space like a halo made of ice and stone. The sixth planet from our sun is not just another world. It is a giant among giants, a planet so immense that it challenges our ability to truly comprehend its scale. More than 700 Earths could fit inside Saturn's vast volume, and yet for all that size, for all that bulk, Saturn carries a secret that seems almost impossible. It is the lightest planet in our entire solar system relative to its size. If you could find an ocean large enough, Saturn would float on the surface like a giant beach ball drifting on summer waters. How can something so massive be so light? The answer lies in what Saturn is made of, in the nature of gas giants and the strange physics of worlds that never formed solid ground beneath their skies. Saturn is not made of rock and metal like Earth. It has no surface you could stand on, no ground that would hold your weight. Instead, it is built from hydrogen and helium, the lightest elements in the universe, the same materials that make up stars. These gases are compressed under tremendous pressure deep within Saturn, squeezed so tightly that hydrogen transforms into something strange and metallic. But in the outer layers where we can see, where the clouds swirl in endless patterns, the planet remains light and airy. Its average density is less than water, less even than some types of wood. For all its grandeur and size, Saturn is built from the whispers of the universe, from the gentlest elements gathered together in enormous quantities. The planet completes one orbit around the Sun every 29.5 Earth years. Right now, as you listen, Saturn is moving through space at nearly 10 kilometers every second, following its ancient path around the star that gives it light. But despite this tremendous speed, its orbit is so vast that it takes nearly 3 decades to complete just one journey around the Sun. If you were born during one of Saturn's years, you would be approaching 30 years old before that planet completed its orbit and returned to the same position in the sky. Time moves differently out there in the cold reaches of the solar system, where the Sun appears smaller and dimmer, where each season lasts for more than 7 Earth years. And Saturn does have seasons just as Earth does. The planet is tilted on its axis, leaning at an angle of nearly 27 degrees. As it orbits the Sun, different parts of Saturn receive different amounts of sunlight, creating seasonal changes in its atmosphere and its magnificent ring system. During Saturn's summer, one hemisphere basks in continuous light while the rings cast shadows across the planet's clouds. During winter, that same hemisphere falls into relative darkness, and the angle of the rings changes as seen from Earth, sometimes appearing wide and open, other times narrowing to a thin line, and occasionally disappearing from view altogether when we see them edge on. One day on Saturn is remarkably short for such a large planet. The giant world spins on its axis once every 10 hours and 33 minutes. This rapid rotation causes Saturn to bulge at its equator and flatten slightly at its poles. If you could watch Saturn spin from a distance, you would see it as an oblate spheroid, wider around its middle than from pole to pole. This bulging equator spins through space at over 35,000 kilometers per hour, creating powerful winds in the atmosphere and contributing to the complex weather patterns that swirl across the planet's face. The rapid spin also generates Saturn's magnetic field, an invisible shield that surrounds the planet and protects it from the solar wind, the stream of charged particles that flows constantly from the Sun. The atmosphere you would see if you looked at Saturn through a telescope is calmer in appearance than Jupiter's, its larger neighbour. Where Jupiter displays bold stripes and swirling storms, Saturn's clouds are more subdued, painted in soft shades of butterscotch and cream, pale yellows and gentle golds. These colours come from trace amounts of ammonia, phosphorus, and other compounds mixed into the hydrogen and helium that makes up most of the atmosphere. The clouds are arranged in bands that circle the planet, driven by winds that blow at different speeds at different latitudes. At the equator, winds can reach speeds of up to 1,800 kilometers per hour, among the fastest winds measured anywhere in our solar system. Deep below those visible clouds, Saturn holds secrets we are only beginning to understand. The pressure increases with depth, growing stronger and stronger until the hydrogen gas transitions into liquid hydrogen. Go deeper still, and the pressure becomes so extreme that hydrogen takes on properties of a metal, conducting electricity and generating the planet's magnetic field. At the very center of Saturn, compressed beneath thousands of kilometers of atmosphere and liquid, there may be a core of rock and metal, perhaps as massive as 10 to 20 Earth masses, though we cannot be certain. No probe has ever penetrated deep into a gas giant, and the conditions there are beyond anything we can easily recreate in laboratories. Saturn is cold in a way that is difficult for us to imagine. At the cloud tops, where our spacecraft have measured temperatures, the thermometer reads -178 degrees Celsius. This is cold enough to freeze carbon dioxide into dry ice, cold enough that even methane would become a solid crystal. Yet despite this bitter cold, Saturn generates heat from within. The planet actually radiates more energy into space than it receives from the Sun. This heat comes from the slow gravitational compression of the planet itself, from helium rain falling deep within Saturn's interior, releasing energy as it descends through the layers of hydrogen. Saturn is cooling slowly, releasing the primordial heat left over from its formation billions of years ago, a dying ember from the birth of the solar system. The gravity at Saturn's cloud tops is slightly stronger than Earth's gravity. If you could somehow stand on the surface of those clouds, if they were solid enough to support your weight, you would feel about 6% heavier than you do on Earth. A person weighing 100 kilograms on Earth would weigh about 106 kilograms at Saturn's cloud tops. But of course, there is no surface to stand on. You would fall through those clouds, sinking deeper and deeper into increasing pressure and heat, your body eventually crushed by forces that build with every kilometer of descent. Saturn formed 4.5 billion years ago from the same cloud of gas and dust that gave birth to the Sun and all the other planets. In the early solar system, as the Sun ignited and began to shine, material in the surrounding disk began to clump together. Rocky materials and metals condensed in the inner regions where temperatures were high, forming the terrestrial planets like Earth and Mars. But farther out, beyond what we call the frost line, temperatures were cold enough for ice to form. Here, in this frozen region, Saturn began to grow. A core of rock and ice accumulated first, perhaps 10 times the mass of Earth. This core's gravity pulled in the surrounding gas, hydrogen and helium that filled the early solar system. The process accelerated as the planet grew larger, its gravity becoming stronger, pulling in more and more material until Saturn reached its current enormous size. When Saturn formed, it was much hotter than it is today, glowing with the heat of formation, perhaps even bright enough to have been considered a failed star by some definitions, though it never accumulated enough mass to ignite nuclear fusion in its core. Over billions of years it has cooled, settling into the quiet giant we see today. But that cooling continues. Every year Saturn radiates away more of its internal heat, and it will continue to do so for billions of years to come, growing slowly colder and dimmer as the universe ages around it. The planet has been known to humanity since ancient times. Our ancestors looked up at the night sky and noticed 5 points of light that moved among the fixed stars. Mercury, Venus, Mars, Jupiter, and Saturn were visible to the naked eye, wandering across the constellations through the course of months and years. Saturn was the slowest of these wanderers, taking nearly 30 years to complete its journey through the zodiac. The ancient Romans named it after Saturn, the god of time and agriculture, perhaps because of its slow, steady movement across the sky. The Greeks called it Kronos, after the Titan who ruled during the mythological Golden Age. For thousands of years, humans watched Saturn without knowing its true nature. They saw only a yellowish point of light, brighter than most stars but dimmer than Jupiter, moving with patient slowness through the heavens. No one knew it was a giant planet. No one suspected the rings. No one imagined the dozens of moons that circle it in the darkness. Saturn kept its secrets, waiting in silence for the invention of the telescope and the curiosity of astronomers who would turn their instruments toward the heavens and begin to unlock the mysteries of the worlds beyond Earth. Before we continue deeper into Saturn's story, before we explore the rings that make it so distinctive and the moons that orbit in its shadow, take a moment to imagine the reality of this distant world. Right now, as you rest and listen, Saturn is out there. If it is night where you are, it might be visible in your sky, a steady golden point among the stars. Light is travelling from the Sun to Saturn, taking more than an hour and 20 minutes to cross that vast distance. That light reflects off the clouds and rings and begins its journey back toward Earth, travelling for another hour and 20 minutes before finally reaching us, carrying information about a world so different from our own that it challenges everything we think we understand about planets. Saturn is real. It is there. And everything we are about to explore together is not fiction or fantasy, but the actual nature of a place that exists in our universe, waiting to be understood. The rings of Saturn are perhaps the most beautiful structure in the solar system. They circle the planet in a thin disk, stretching out for hundreds of thousands of kilometers, yet measuring in most places only tens of meters thick. If you could shrink them down proportionally, they would be thinner than a sheet of paper. They catch the sunlight and scatter it in countless directions, making Saturn shine with a brilliance that outshines the planet itself when viewed from certain angles. These rings have captured human imagination ever since they were first glimpsed through early telescopes, and even now, after decades of study by spacecraft, they continue to hold mysteries that scientists are still working to unravel. The rings are made primarily of water ice. Billions upon billions of particles orbit Saturn in formation, ranging in size from tiny grains smaller than sand to enormous chunks larger than houses. Some pieces are the size of pebbles, others like boulders, and a few are small moons in their own right, kilometers across. Each particle follows its own orbit around Saturn, moving at speeds determined by its distance from the planet. The inner particles orbit faster, while the outer ones move more slowly, and this differential motion would cause the rings to spread and dissipate over time, if not for the complex gravitational interactions that hold them together. There are actually several distinct rings, separated by gaps and divisions. The most prominent rings, visible even through small telescopes from Earth, are labelled with letters. The A ring is the outermost of the bright rings, separated from the B ring by the Cassini division, a gap of nearly 5,000 kilometers where the ring material is sparse. The B ring is the brightest and most massive of all Saturn's rings, containing the bulk of the ring material. Inside the B ring lies the C ring, sometimes called the crepe ring because it appears more transparent and delicate than its brighter neighbours. These main rings extend from about 7,000 kilometres above Saturn's cloud tops to more than 80,000 kilometres out into space. But the ring system does not end there. The D ring lies inside the C ring, closer to Saturn, though it is so faint it was not discovered until space probes began studying the planet up close. Extending outward beyond the A ring is the narrow F ring, a thin strand held in place by the gravitational shepherding of two small moons. Still farther out, almost invisible from Earth, is the enormous E ring, a diffuse torus of microscopic ice particles that extends from the orbit of the moon Mimas to beyond the orbit of Titan. This ring is fed by geysers on the moon Enceladus, which spray water ice into space, creating a tenuous halo around Saturn. Each ring has its own character and structure. The B ring is so dense in places that it is nearly opaque, blocking light from stars when they pass behind it. The A ring contains several narrow gaps, including the Encke gap and the Keeler gap, which are kept clear by small moonlets orbiting within the rings themselves. These moonlets act like cosmic lawnmowers, their gravity sweeping up nearby particles and creating clear zones in the ring material. The C-ring has a ghostly, translucent quality, allowing sunlight to pass through while still scattering enough light to be visible. Within the C-ring, astronomers have identified wave-like structures called ringlets, narrow bands of material separated by even narrower gaps. The rings are not solid structures, but rather countless individual particles, each one a tiny moon following the laws of orbital mechanics. When viewed from a distance, they appear smooth and continuous, but up close they reveal their true nature as a vast swarm of orbiting ice. The particles collide with each other constantly, very gently, at speeds of just millimeters per second. These collisions help keep the rings flat, damping out any vertical motion and confining the particles to a thin plane. Despite these collisions, the rings are mostly empty space. If you could fly through them, you would likely pass through without hitting anything, though the overall density of particles would depend on which ring you chose to traverse. Scientists have long debated the origin of Saturn's rings. One possibility is that they are ancient, dating back to the formation of the solar system itself, primordial material that was prevented from coalescing into a moon by Saturn's powerful tidal forces. Another theory suggests the rings are much younger, perhaps only a few 100 million years old, created when a moon or comet ventured too close to Saturn and was torn apart by tidal forces. Evidence from the Cassini spacecraft suggests the rings may indeed be relatively young, perhaps formed during the age of dinosaurs on Earth. The rings appear too clean, too free of the dust and debris that would accumulate over billions of years in the busy environment of the solar system. Within the rings themselves, spacecraft have discovered structures that change and evolve. Propeller-shaped disturbances appear where moonlets embedded in the rings create wakes in the surrounding material. Spokes appear in the B-ring, dark radial features that rotate with the planet's magnetic field rather than following the orbital motion of the ring particles. These spokes may be caused by dust levitated above the ring plane by electrical forces, creating temporary shadows. The spokes were first noticed in images from the Voyager spacecraft and later confirmed by Cassini observations. The ring system casts shadows on Saturn's clouds when the sun angle is right. These shadows are enormous, stretching across thousands of kilometers of the planet's surface. During Saturn's equinox, when the sun shines edge onto the rings, the shadows disappear, and the rings themselves seem to vanish when viewed from Earth, becoming nearly invisible as we see them edge on. This happens once every 15 years, during Saturn's spring and autumn, and it allows astronomers to search for new moons and structures that are normally hidden in the glare of the rings' reflected light. Temperature in the rings varies depending on the particle's composition and location. The ice particles can range from about -180 degrees Celsius to much warmer temperatures when in direct sunlight. During Saturn's day, particles on the sunward side can warm significantly, while those in shadow or during Saturn's night remain frozen. This temperature variation creates subtle changes in the ring's appearance and may drive processes that help maintain their structure over time. The rings are not perfectly circular. Some parts are slightly elliptical, wobbling in and out as they orbit Saturn. These eccentricities are caused by gravitational interactions with Saturn's moons, which pull on the ring material and create waves and spirals. Some of these waves are beautiful spiral density patterns, similar to the spiral arms seen in galaxies, where material bunches up in certain areas and spreads out in others. The mathematical patterns that describe these waves are the same equations used to study galaxies and other cosmic structures, a reminder that gravity works the same way at every scale. The total mass of Saturn's rings is substantial but surprisingly small compared to Saturn itself. If you gathered all the ring material together, it would form a moon perhaps 100 kilometers across, much smaller than most of Saturn's major moons. The rings may be the remnants of such a moon, shattered by an impact or torn apart by tides. All that mass spread across such a vast area creates the illusion of something much larger, like a thin sheet of gold leaf that covers a large area but weighs very little. Within the ring system, some particles orbit in resonance with Saturn's moons, meaning they complete a certain number of orbits in the same time it takes a moon to complete its orbit. These resonances create gaps where the gravitational tugs from moons prevent particles from maintaining stable orbits. The Cassini division, the largest gap in the rings, is maintained partially by a resonance with the moon Mimas. Any particle trying to orbit in the Cassini division would be repeatedly tugged by Mimas's gravity at the same point in its orbit, eventually forcing it to move to a different orbit where the resonance does not occur. Looking at Saturn's rings from different angles reveals different features. When viewed from above or below the ring plane, they appear as concentric circles, bright and distinct. When viewed edge-on, they nearly disappear, revealing their incredible thinness. When viewed at intermediate angles, they show their three-dimensional structure, with some rings appearing to overlap others in a complex layering. Each viewing angle tells astronomers something different about the ring's structure and composition. The rings also respond to Saturn's magnetosphere, the region of space dominated by the planet's magnetic field. Charged particles from the solar wind and from Saturn's moons interact with the ring particles, sometimes creating auroras and electrical phenomena in the ring system. The interaction between charged particles and ice creates complex chemistry, slowly darkening some of the ice and creating new molecules. Over time, this space weathering changes the appearance and properties of the ring material. One of the most beautiful phenomena in Saturn's rings is the way they refract and scatter light. Ice is an excellent reflector of sunlight, especially in the visible and ultraviolet wavelengths. The rings reflect so much light that they contribute significantly to Saturn's overall brightness as seen from Earth. When the sun passes behind the rings from our perspective, the backlit rings glow with transmitted light, revealing details and structures that are invisible when viewing the sunlit side. These backlit views show that the rings have much more fine structure than appears at first glance, with countless ringlets and gaps woven throughout. The age of the rings remains one of the great questions about Saturn. If they are ancient, they have somehow avoided being darkened and contaminated by billions of years of meteorite impacts and dust accumulation. If they are young, we are fortunate to live at a time when Saturn has rings, because they may disappear in the future, either falling into Saturn or spreading out into space. Current estimates based on Cassini data suggest the rings may be between 10 million and 100 million years old, young in cosmic terms, but ancient by human standards. Standing on one of the larger ring particles, if such a thing were possible, you would see a strange sight. Other ice chunks would surround you in every direction, some near and some far, all slowly orbiting Saturn in silence. The planet would loom above you, filling half the sky with its butterscotch clouds and subtle bands. Other particles would occasionally drift past, moving at slightly different speeds, sometimes colliding gently with the ground beneath your feet. In the distance, Saturn's moons would shine like bright stars, some close enough to show as tiny disks. The sun would be distant and smaller than it appears from Earth, but still bright enough to illuminate the ice around you in every direction. It would be a world of ice and light, silence and slow motion, perhaps the most beautiful place to float in all the solar system. Saturn's atmosphere is a realm of winds and storms, of clouds that swirl in patterns both elegant and violent. Though it appears calm compared to the dramatic storms of Jupiter, Saturn's atmosphere holds its own wonders, from gentle banding to powerful hexagonal vortices that have no parallel anywhere else in the solar system. The atmosphere you see when looking at Saturn is not a surface, but rather the top layer of clouds, beyond which the gas grows denser and denser until eventually it transitions into liquid deep below. Everything visible is atmosphere, and that atmosphere extends downward for thousands of kilometers. The primary components of Saturn's atmosphere are hydrogen and helium, the same elements that make up the Sun and most of the universe. Roughly 96% of Saturn's atmosphere is hydrogen, with most of the remaining portion being helium, but it is the trace elements, the tiny fractions of other substances, that give Saturn its color and create its weather. Ammonia ice crystals form clouds in the upper atmosphere, creating the pale yellow color we see from Earth. Deeper down, clouds of ammonium hydrosulfide add different hues. Still deeper, where pressures are higher, water ice clouds may form, though these are hidden far below the visible surface. Temperature in Saturn's atmosphere varies with altitude and latitude. At the level where pressure equals 1 bar, roughly equivalent to sea level pressure on Earth, temperatures average around -139 degrees Celsius. Higher in the atmosphere, in the stratosphere, temperatures can drop even lower or rise slightly depending on the absorption of solar radiation. Near the equator, temperatures are slightly warmer than at the poles, driving convection and creating weather patterns. These temperature differences, combined with Saturn's rapid rotation rotation create the wind systems that circle the planet. The winds on Saturn are among the fastest in the solar system. At the equator, winds blow eastward at speeds reaching 1,800 kilometers per hour, faster than the speed of sound on Earth. These winds are not like winds on Earth, which are driven primarily by heating from the sun. Instead, Saturn's winds are driven more by heat from the planet's interior, creating a deeper, more consistent pattern than we see on our homeworld. The jet streams on Saturn maintain their speed and direction for years, sometimes decades, showing that the weather patterns are rooted deep in the atmosphere where the day-to-day changes at the surface cannot disturb them. Saturn displays subtle banding in its clouds, with different zones and belts circling the planet at different latitudes. These bands are less dramatic than Jupiter's, muted in colour and gentler in contrast, but they follow similar patterns. In the zones, where gas rises from below, clouds form at higher altitudes and appear brighter. In the belts, where gas descends, the clouds are lower and appear slightly darker. The boundaries between these bands are jet streams, where the fastest winds blow. Each band is essentially a separate weather system, isolated from its neighbours by the shearing winds that separate them. The poles of Saturn hold some of the planet's most intriguing features. At the North Pole, there is a hexagonal cloud pattern, a six-sided jet stream that surrounds the polar region. Each side of this hexagon stretches approximately 13,800 kilometers, larger than the diameter of Earth. The hexagon has been observed since the Voyager spacecraft flew by Saturn in the early 1980s, and it persists today, rotating with the planet every 10 hours and 39 minutes. The hexagon is a standing wave pattern in the jet stream, created by the interaction of winds at different latitudes. Nothing quite like it has been seen anywhere else in the solar system. It remains stable year after year, its six sides nearly perfect, its angles sharp, as though some cosmic artist had drawn it with a ruler. Inside the hexagon is a massive storm system centered on the North Pole itself. This storm is larger than Earth, with an eye reminiscent of a hurricane surrounded by swirling clouds that spiral inward. Unlike hurricanes on Earth, which draw their energy from warm ocean water and dissipate when they move over land, Saturn's polar storm draws energy from the heat of the planet's interior and may have been raging for decades or centuries. It has winds exceeding 500 kilometers per hour and features that change and evolve over months and years. At the South Pole, there is no hexagon, but instead another massive storm system, similar in structure to the northern storm. Both poles are darker than the surrounding atmosphere, and both show evidence of complex vertical structure where gases sink and rise in towering convective columns. The poles are colder than the equatorial regions, and during winter, when one pole faces away from the sun for years at a time, that hemisphere can cool significantly, creating seasonal changes in the atmosphere. Saturn occasionally develops large storms that erupt from the depths and spread across vast areas. These great white spots, as they are called, appear roughly once every 30 years during Saturn's northern hemisphere summer. They begin as small bright spots and then spread eastward, driven by the planet's powerful jet streams, eventually encircling the entire planet in a white band before gradually fading over months. These storms may be caused by convection from deep in the atmosphere, where warmer material rises and breaks through the upper cloud layers. The most recent great white spot appeared in late 2010 and was observed extensively by amateur astronomers and the Cassini spacecraft. Lightning has been detected in Saturn's atmosphere, though it is different from lightning on Earth. Saturn's lightning occurs deep in the atmosphere, in the water cloud layer far below the visible cloud tops. These lightning storms can last for months, flickering with flashes thousands of times more powerful than lightning on Earth. The radio emissions from these storms can be detected by spacecraft, allowing scientists to study weather patterns deep in the atmosphere that are otherwise invisible. The presence of lightning tells us that there is dynamic convection happening far below, with updrafts and downdrafts powerful enough to generate electrical charge separation. The colours of Saturn are subtle but beautiful. Through a small telescope, Saturn appears pale yellow or butterscotch. Larger telescopes and spacecraft reveal more detail, showing bands of slightly different hues, cream and tan and pale gold. These colours come from the chemicals in the clouds and the way they absorb and reflect sunlight. Ammonia crystals are white, but when mixed with tiny amounts of phosphorus or other compounds, they take on the warmer colours we observe. Methane in the upper atmosphere absorbs red light, giving the planet a slightly bluish tint in some wavelengths. The exact chemistry that creates Saturn's specific colors is still being studied, but it involves complex photochemistry driven by sunlight breaking apart molecules and allowing them to recombine in new forms. Hazes in Saturn's upper atmosphere also contribute to its appearance. These hazes are made of tiny particles created when sunlight breaks apart methane molecules, allowing carbon atoms to combine into more complex hydrocarbons. These organic molecules form a smog-like layer high in the atmosphere, scattering light and creating a gentle veil over the deeper clouds. Similar hazes are found on Saturn's moon Titan, where they create an opaque orange atmosphere. On Saturn, the hazes are thinner and less opaque, but they still affect the planet's color and reflectivity. The atmosphere is not still. It churns constantly with convection, with gases rising from the warm interior and cooling as they rise, forming clouds and then descending again after releasing their heat. This convection creates the banded structure and drives the weather patterns. On Earth, convection is powered by the sun heating the surface, but on Saturn, internal heat plays a larger role. This means Saturn would still have weather even if the sun went dark, though the patterns would certainly change. The pressure in Saturn's atmosphere increases rapidly with depth. At the cloud tops, pressure is similar to Earth's upper atmosphere, a fraction of a bar. 100 kilometers down, pressure equals Earth's sea level. Continue downward and the pressure climbs to 10 bars, 100 bars, 1000 bars. Eventually you reach a region where the increasing pressure and temperature cause hydrogen gas to transition into liquid hydrogen. There is no clear boundary, no surface where gas becomes liquid, but rather a gradual transition as the density increases smoothly with depth. This is a world without ground, where the atmosphere simply becomes denser and denser until it is no longer gas but liquid, and deeper still where liquid hydrogen takes on metallic properties. Studying Saturn's atmosphere helps scientists understand atmospheric dynamics, not just on gas giants, but on all planets, including Earth. The physics of jet streams, the formation of storms, the behavior of rotating fluids, all these phenomena follow the same mathematical laws, whether they occur on Earth, Saturn, or elsewhere. Saturn serves as a giant laboratory where we can observe atmospheric processes in conditions very different from our own world, helping us refine our models and deepen our understanding of how atmospheres behave. The clouds themselves are thought to be organized in layers at different depths, with each layer corresponding to a different chemical compound reaching its condensation point. Highest and most visible are the ammonia ice clouds. Below these would be ammonium hydrosulfide clouds, and deeper still, clouds of water ice. Each layer has its own characteristics, its own temperature and pressure regime, and contributes to the overall structure of the atmosphere. Observing how clouds move at different levels tells scientists about winds at different depths, revealing the three-dimensional structure of Saturn's weather. Seasonal changes do occur on Saturn despite the planet's distance from the Sun. As the seasons progress, the amount of sunlight each hemisphere receives changes, altering temperatures and driving shifts in cloud patterns. When the Cassini spacecraft arrived at Saturn in 2004, the southern hemisphere was experiencing summer. Over the years of the mission, the seasons changed, and by the time Cassini's mission ended in 2017, the northern hemisphere had moved into summer. These seasonal changes were observed in real time, showing how the atmosphere responds to shifting sunlight over the course of Saturn's long year. Auroras occur at Saturn's poles, just as they do on Earth. These shimmering lights are caused by charged particles from the solar wind and from Saturn's moons being funneled along magnetic field lines into the polar regions. When these particles collide with molecules in the upper atmosphere, they cause them to glow, creating curtains and arcs of light visible in ultraviolet wavelengths. Saturn's auroras are more variable than Earth's, sometimes flaring brightly when the solar wind is strong, other times fading to faint glows. They are one more reminder that Saturn is connected to the rest of the solar system through invisible magnetic and electric fields that channel energy across vast distances. The atmosphere extends upward from the clouds into an exosphere, a tenuous region where atoms and molecules move on ballistic trajectories rather than colliding frequently with neighbors. Here, the atmosphere gradually fades into the near vacuum of space. The boundary is not sharp, but rather a gradual thinning, and some atoms from Saturn's atmosphere escape into space, lost forever to the solar wind. Over billions of years, Saturn has lost a tiny fraction of its atmosphere this way, but the planet is so massive that this loss is negligible. The atmosphere will remain for billions of years to come. Perhaps one of the most humbling thoughts is that if you could somehow survive the cold and pressure and float in Saturn's atmosphere at a level where the pressure equaled Earth's sea level, you would be surrounded by hydrogen gas. You would see clouds above and below you, extending in every direction to the horizon and beyond. The sky would be filled with colour, soft yellows and creams, and if you were near the rings, you might see them arcing across the sky like a bridge to nowhere. Wind would rush past you at hundreds of kilometers per hour, yet there would be no sound, only the rushing presence of gas moving at incredible speeds. It would be a place of beauty and danger, a world unlike any we have known, and yet it would be real as the ground beneath your feet right now, existing at this very moment more than 1 billion kilometers away. Saturn is not alone in its journey around the Sun. It is accompanied by a vast family of moons, more than 80 known worlds, that orbit the ringed planet in a complex dance of gravity. These moons range from tiny, irregular chunks of rock and ice only a few kilometers across to massive worlds that rival the planet Mercury in size. Each moon has its own character, its own story, and together they form one of the most diverse and fascinating collections of natural satellites in the entire solar system. As you continue to relax and let these words carry you into deeper calm, we will begin to explore these distant companions, understanding how they formed, how they interact, and why they matter to our understanding of the solar system. The moons of Saturn can be divided into several groups based on their orbits and origins. The innermost moons orbit within or near the rings themselves, small bodies that shepherd ring particles and create gaps in the icy disk. Beyond the rings are the major moons, large spherical worlds with complex surfaces, and in some cases subsurface oceans. Farther out are the irregular moons, captured asteroids and comets that orbit Saturn in distant, often retrograde paths. Each group tells a different part of Saturn's history, from the formation of the planet to more recent captures from the outer solar system. The largest of Saturn's moons is Titan, a world so substantial that it deserves its own extended discussion, which we will turn to soon. But even setting Titan aside, Saturn has many remarkable moons. Rhea is the second largest, a heavily cratered world of ice about 1,500 kilometers in diameter. Its surface is ancient, covered with impact craters from billions of years of bombardment, yet it also shows brighter rays extending from some craters, evidence of relatively recent impacts that exposed fresh ice. Rhea may have a tenuous ring system of its own, though this remains uncertain. If confirmed, Rhea would be the only moon in the solar system known to have rings. Iapetus is one of Saturn's strangest moons. It has a distinctive two-toned appearance, with one hemisphere as bright as snow and the other as dark as coal. The dark material is concentrated on the leading hemisphere, the side that faces forward as Iapetus orbits Saturn, and is thought to be debris that has gradually accumulated as the moon sweeps through its orbit. The source of this dark material may be other, more distant moons, or it may have been generated by processes on Iapetus itself. The boundary between the bright and dark regions is sharp in some places and gradual in others, creating a surreal landscape. Iapetus also has a prominent equatorial ridge, a mountain range that circles almost the entire moon along its equator, rising more than 20 kilometers above the surrounding terrain. The origin of this ridge is still debated, but it may be related to ancient tectonic activity or the remnants of a collapsed ring system. Dione and Tethys are medium-sized icy moons with heavily cratered surfaces. Dione shows evidence of past tectonic activity, with long fractures and cliffs cutting across its ancient terrain. Some regions appear to have been resurfaced by cryovolcanism, where ice and water erupted from below and covered older features. Tethys has a massive crater called Odysseus, nearly 400 kilometers across, so large that it dominates one hemisphere of the moon. The impact that created this crater must have come close to shattering Tethys entirely. The moon also has a vast canyon system called Ithaca Chasma, which extends for more than 2,000 kilometers across the surface, perhaps formed by tidal stresses or the freezing of a subsurface ocean. Enceladus is small but extraordinary. Though only about 500 kilometers in diameter, this tiny moon is one of the most geologically active bodies in the solar system. Its south polar region is warm, with temperatures about 50 degrees higher than would be expected from sunlight alone. From long fractures near the South Pole, giant geysers erupt, spraying water ice and vapor into space at speeds of hundreds of meters per second. These geysers create a plume that extends thousands of kilometers above Enceladus, feeding Saturn's E-ring with fresh ice particles. The presence of these geysers tells us that Enceladus has liquid water beneath its icy surface, kept warm by tidal heating as Saturn's gravity flexes the moon's interior. This subsurface ocean may be in contact with a rocky core, creating conditions that could, in theory, support microbial life. Enceladus has become one of the prime targets in the search for life beyond Earth. Mimas is famous for looking remarkably like the Death Star from Star Wars, thanks to a massive crater called Herschel that dominates one hemisphere. This crater is about 130 kilometers across, nearly one-third the diameter of Mimas itself. The impact that created Herschel must have come close to destroying the moon, and shock waves from the impact created cracks and grooves on the opposite side of Mimas. Despite its small size, Mimas plays an important role in sculpting Saturn's rings. Its gravity creates the Cassini division, the large gap between the A and B rings, through orbital resonance effects. Hyperion is a strange, irregularly shaped moon with a sponge-like appearance. Its surface is covered with deep craters and the material seems unusually porous, giving it a lower density than would be expected. Hyperion tumbles chaotically as it orbits Saturn, its rotation unpredictable due to gravitational interactions with Titan and the irregular shape of the moon itself. Observing Hyperion over time reveals an object that spins and wobbles in ways that seem almost random, though they are governed by the strict laws of celestial mechanics. Phoebe is a large, irregular moon that orbits Saturn in a retrograde direction, meaning it moves opposite to the direction of Saturn's rotation. This retrograde orbit tells us that Phoebe was not formed in orbit around Saturn, but was instead captured from elsewhere, probably from the Kuiper belt beyond Neptune. Its composition is different from Saturn's inner moons, darker and more carbonaceous, rich in organic molecules. Phoebe represents a sample of material from the outer solar system, brought close to Saturn by gravitational interactions billions of years ago. The smaller moons closer to the rings play crucial roles in shaping and maintaining the ring structure. Pan and Daphnis orbit within gaps in the rings, their gravity creating wakes and wave-like patterns in the surrounding ring material. These small moons, only tens of kilometers across, have accumulated ring particles around their equators, giving them a distinctive shape that has been compared to flying saucers or ravioli. Prometheus and Pandora are shepherd moons that orbit on either side of the narrow F ring, their gravity constraining the ring particles and keeping the ring from dispersing. The F ring itself shows kinks, braids, and clumps that change over time, evidence of the complex gravitational dance between the moons and the ring material. Many of Saturn's smaller, irregular moons may be fragments of larger bodies that were broken apart by collisions. They orbit in clusters at similar distances from Saturn, suggesting they share a common origin. Some orbit in the same direction as Saturn's rotation, while others move in retrograde orbits. These irregular moons are likely captured objects, asteroids or comets that wandered too close to Saturn and were caught by its gravity. Over time, some of these captured objects may have collided with each other, creating families of related fragments. The discovery of Saturn's moons has been an ongoing process that continues to this day. The first moon, Titan, was discovered in 1655 by Christian Huygens. Over the following centuries, other moons were gradually discovered as telescopes improved. Iapetus, Rhea, Dione, and Tethys were discovered in the late 1600s and early 1700s. Mimas and Enceladus were found in the late 1700s. Hyperion was discovered in the 1850s. As technology advanced, more moons were found, especially the smaller ones that are too faint to see from Earth without powerful telescopes. The Voyager spacecraft discovered several new moons during their flybys in the 1980s, and the Cassini mission discovered dozens more during its 13 years orbiting Saturn. Even now, the count of Saturn's moons continues to grow. In 2019, astronomers announced the discovery of 20 previously unknown moons, bringing the total to 82 at that time, surpassing Jupiter's count. Most of these newly discovered moons are small, irregular objects orbiting far from Saturn, but each one adds to our understanding of the Saturn system and the processes that shaped it. The gravitational interactions among Saturn's many moons create resonances that affect their orbits and their interiors. Some moons are locked in orbital resonances with each other, where their orbital periods are related by simple ratios. For example, Enceladus and Dione are in a 2-to-1 resonance, meaning Enceladus completes 2 orbits for every 1 orbit of Dione. These resonances can pump energy into the moons through tidal flexing, helping to keep their interiors warm and geologically active. Without these resonances, Enceladus might be a dead, frozen world instead of the active moon with geysers that we observe today. The moons also interact with Saturn's magnetosphere, the region of space dominated by Saturn's magnetic field. As the magnetosphere rotates with Saturn, it sweeps past the moons, and electrically charged particles in the magnetosphere collide with the surfaces of the moons, causing chemical reactions and slowly altering the surface properties. Some moons, like Enceladus, contribute material to the magnetosphere through their geysers, creating a torus of neutral and ionized particles that orbit Saturn at the moon's orbital distance. The variety of Saturn's moons is astonishing. Some are icy and pristine, their surfaces reflecting sunlight like fresh snow. Others are dark and cratered, their surfaces ancient and unchanged for billions of years. Some show evidence of geological activity with fractures, flows, and fresh surfaces indicating recent changes. Others seem dead, their surfaces recording only the slow accumulation of impact craters over eons. Together, these moons form a natural laboratory for studying planetary processes, from impact cratering to tidal heating, from cryovolcanism to atmospheric formation. If you could stand on one of Saturn's smaller inner moons, perhaps Janus or Epimetheus, you would see Saturn dominating the sky, enormous and beautiful, its rings stretching across the heavens like a delicate arch. Other moons would be visible, some as bright points of light, others as crescents or gibbous phases. The sun would shine distantly, providing enough light to see by but feeling cold and remote. The ground beneath your feet would be ice, ancient and hard, perhaps covered in a layer of fine dust from countless micrometeorite impacts. In the silence of space, without air to carry sound, you would watch this ballet of worlds in perfect quiet, each moon and ring following the invisible pathways laid down by gravity billions of years ago. Among all of Saturn's moons, one stands apart in size, complexity, and mystery. Titan is the second largest moon in the entire solar system, larger than the planet Mercury, and the only moon with a substantial atmosphere. It is a world shrouded in orange clouds, a place where methane rains from the sky and rivers of liquid hydrocarbons carve channels through landscapes of water ice as hard as rock. Titan is so remarkable, so unique among moons, that it deserves our focused attention as we continue this gentle journey through the Saturn system. As you settle deeper into rest, imagine traveling beyond the rings and the smaller moons, out to where Titan orbits, and let us explore what makes this distant world so extraordinary. Titan is large, with a diameter of about 5150 kilometers, making it about 50% wider than Earth's moon and about 40% the diameter of Earth itself. It is the only moon in our solar system larger than Titan is Mercury, though Jupiter's moon Ganymede holds the title of largest overall. Despite its size, Titan's density is lower than Earth's moon, suggesting it is made of a mixture of ice and rock rather than being predominantly rocky like the terrestrial planets. The lower density means that Titan has less mass than its size would suggest, and the surface gravity is only about 14% of Earth's gravity. A person weighing 70 kilograms on Earth would weigh less than 10 kilograms on Titan. The most striking feature of Titan is its atmosphere. No other moon in the solar system has anything like it. Titan's atmosphere is thick, with a surface pressure about 50% greater than Earth's sea level pressure. It extends hundreds of kilometers above the surface, far higher than Earth's atmosphere, because Titan's lower gravity allows it to hold onto a more extended envelope of gas. The atmosphere is primarily nitrogen, making up about 98% of the total, with most of the remainder being methane and small amounts of hydrogen and other trace gases. This nitrogen-rich composition is similar to Earth's atmosphere, though Earth has oxygen where Titan has methane. The methane in Titan's atmosphere plays a role similar to water in Earth's atmosphere. It cycles through different phases, existing as a gas in the atmosphere, condensing into liquid in clouds, falling as rain, flowing in rivers, and collecting in lakes and seas on the surface. This methane cycle is the only place in the solar system besides Earth where we know liquids stably exist on the surface and cycle through the atmosphere. On Earth, the cycle involves water. On Titan, it involves methane and ethane, but the processes are remarkably similar: evaporation, cloud formation, precipitation, runoff, and collection in bodies of liquid. The atmosphere gives Titan its distinctive orange color. The haze that blankets the moon is created by photochemistry in the upper atmosphere, where sunlight breaks apart methane molecules and allows the carbon and hydrogen atoms to recombine into more complex organic molecules. These molecules, including tholins and other hydrocarbons, form tiny particles that accumulate in a thick haze layer, giving Titan its opaque appearance. From space, Titan looks like a featureless orange ball, its surface completely hidden beneath the clouds. Only by using infrared light or radar can we peer through the haze and see the landscape below. Beneath the haze, Titan's surface is a world of varied terrain. There are vast equatorial sand dunes made not of silica sand like Earth's deserts, but of organic particles, hydrocarbons created in the atmosphere and rained down onto the surface over millions of years. These dunes stretch for hundreds of kilometers, forming parallel lines shaped by Titan's winds. There are mountainous regions, highlands of water ice that rise above the surrounding plains. There are impact craters, though fewer than expected, suggesting that Titan's surface is relatively young and active, with erosion and other processes erasing older features. The polar regions of Titan hold lakes and seas of liquid methane and ethane. These are not small puddles, but substantial bodies of liquid, some of them comparable in size to Earth's Great Lakes. The largest, Kraken Mare, is bigger than the Caspian Sea on Earth. These seas are fed by rivers that flow from the highlands, carving valleys and deltas as they transport liquid hydrocarbons from one region to another. The liquid is cold, around -179 degrees Celsius, but it flows and behaves much like water does on Earth. Waves may ripple across the surfaces of these seas, driven by Titan's winds, though they would be gentle due to the thick atmosphere and low gravity. Titan experiences seasons as Saturn orbits the Sun. Each season on Titan lasts about 7.5 Earth years, and the changing seasons affect the distribution of methane. During northern summer, more methane evaporates from the northern lakes and is transported toward the southern hemisphere, where it condenses and falls as rain. During southern summer, the process reverses. Over the course of a Titan year, the methane moves back and forth between the hemispheres, creating seasonal weather patterns and redistributing liquids across the surface. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, studied Titan extensively. It flew by Titan more than 120 times using radar to map the surface and instruments to study the atmosphere. Cassini also carried a probe called Huygens, built by the European Space Agency, which was released to descend through Titan's atmosphere and land on the surface. In January 2005, Huygens became the first spacecraft to land in the outer solar system. During its descent, it took photographs showing a landscape of rounded stones and drainage channels, evidence of liquid flow. After landing, it transmitted data for about 90 minutes before its batteries died, sending back images of a dimly lit surface covered in pebbles of ice, with a hazy orange sky above. Beneath Titan's surface, scientists believe there is a subsurface ocean of liquid water mixed with ammonia. This ocean would lie beneath a crust of ice, kept liquid by heat from Titan's interior and by the antifreeze properties of ammonia. Evidence for this ocean comes from measurements of Titan's shape and gravitational field, which suggest that the interior has layers with different densities. The presence of a subsurface ocean raises the tantalizing possibility that Titan could harbor life, though any life in the cold, ammonia-rich water would be very different from life on Earth. Separately, some scientists speculate about the possibility of life based on liquid methane on Titan's surface, a form of life so alien it would use entirely different chemistry than Earth life. The surface of Titan is shaped by processes that seem familiar, yet occur under completely alien conditions. Erosion by wind and liquid creates familiar-looking features like dunes, river valleys, and coastlines, but these features are made of materials that would be frozen solid on Earth. The rocks on Titan are water ice, as hard as granite in Titan's cold environment. The liquids are methane and ethane, which would be gases at Earth's temperatures. The organic particles that make up the dunes would be sticky, tarry substances if brought to Earth. Everything is chemically shifted, yet the physical processes follow the same laws. Titan's atmosphere creates a greenhouse effect, warming the surface by a few degrees above what it would be without an atmosphere. However, the thick haze also blocks much of the sunlight, so the surface is dim even at noon. The amount of sunlight reaching Titan's surface is only about 1% of what reaches Earth's surface, roughly equivalent to twilight on Earth. Despite this dimness, there is enough light to see by, and the Huygens probe's cameras captured detailed images during its descent. The winds on Titan are generally gentle near the surface, blowing at only a few meters per second. Higher in the atmosphere, winds can be faster, and there are jet streams similar to those on Earth and other planets with atmospheres. The thick atmosphere and slow winds mean that weather on Titan is gentle compared to the violent storms of Jupiter or Saturn. Clouds form and dissipate slowly. Rain falls in large drops due to the low gravity and thick atmosphere, and when it hits the ground, it creates familiar patterns of erosion and deposition. One of the most intriguing aspects of Titan is its abundance of organic molecules. The atmosphere is a natural laboratory for organic chemistry, with sunlight driving reactions that create complex molecules from simple starting materials. Tholins, the particles that create the orange haze, are organic polymers that contain carbon, hydrogen, nitrogen, and oxygen. These molecules rain down onto the surface, accumulating over geological time into layers that may be tens of meters thick in some places. If we could bring these organic materials to Earth and add water and heat, they might form some of the building blocks of life. Titan's surface is essentially covered in prebiotic chemistry, frozen in place by the cold temperatures. The possibility of cryovolcanism on Titan has been suggested based on features that look like volcanic domes and flows. If these are indeed cryovolcanoes, they would erupt not with molten rock but with slushy mixtures of water and ammonia, possibly mixed with methane and other volatiles. The eruptions would be cold, but the dynamics would be similar to volcanic eruptions on Earth, with material rising from the interior, reaching the surface and spreading out in flows. Titan's relationship with Saturn is complex. Tidal forces from Saturn flex Titan's interior, generating heat through friction. This tidal heating, though less extreme than on moons like Io or Enceladus, may contribute to keeping Titan's subsurface ocean liquid. Titan orbits Saturn in just under 16 Earth days, and it is tidally locked, meaning the same side always faces Saturn, just as Earth's moon always shows the same face to Earth. The study of Titan has profound implications for understanding planetary processes throughout the solar system and beyond. Titan shows us what a world with organic chemistry and liquid cycles looks like under very different conditions than Earth. It helps us understand how atmospheres work, how organic molecules form in space, and what factors determine whether a world is habitable. Future missions to Titan are being planned, including a NASA mission called Dragonfly, which will send a rotorcraft to explore multiple sites on Titan's surface, studying the chemistry and searching for signs of past or present life. If you could float in Titan's atmosphere, perhaps suspended beneath a balloon high above the surface, you would see an orange haze in every direction, a soft glow that dims toward the horizon. Below, the landscape would be visible in shades of brown and tan, with darker regions marking the lakes and seas, brighter areas showing the ice highlands. The air would be thick around you, and you would drift slowly with winds that blow steadily but gently. Saturn might be visible as a bright crescent through the haze, massive and beautiful, its rings edge-on and shining like a bright line across the sky. The sun would be a dim point of light, barely brighter than a full moon appears from Earth. It would be a place of muted colours and soft shadows, a world unlike any other, yet somehow familiar in the patterns of its rivers, lakes, and weather. Titan, in all its strangeness, is perhaps the most Earth-like place in the solar system aside from Earth itself, a distant mirror reflecting possibilities we are only beginning to explore. While Titan draws much of the attention among Saturn's moons, the other satellites in this vast system each hold their own fascinations and secrets. Some are geologically active, erupting ice into space. Others are ancient and cratered, silent witnesses to billions of years of cosmic bombardment. A few have odd shapes or unusual compositions, hints of violent origins or complex histories. As we continue our gentle exploration, let us visit some of these remarkable worlds, understanding what makes each one unique and how they contribute to our understanding of Saturn and the solar system as a whole. Enceladus, though we mentioned it briefly before, deserves a closer look because it has become one of the most important targets in the search for extraterrestrial life. This small moon, measuring just over 500 kilometers in diameter, would fit comfortably within the borders of a large country on Earth. Yet despite its size, Enceladus is extraordinarily active. Its south polar region is crossed by 4 prominent fractures called tiger stripes, each about 130 kilometers long and spaced roughly 40 kilometers apart. These fractures are warmer than their surroundings, and from them erupt towering plumes of water vapor and ice particles shooting hundreds kilometers above the surface at velocities that exceed the escape velocity of Enceladus. The Cassini spacecraft flew through these plumes multiple times, sampling their composition. The plumes contain water ice, water vapor, carbon dioxide, methane, ammonia, and simple organic molecules. Salt was also detected, suggesting that the subsurface ocean is in contact with a rocky core where water can leach minerals from the rock. This is significant because on Earth, the interface between water and rock is where chemical energy can be extracted, providing a potential energy source for life. The chemistry detected in the plumes suggests that hydrothermal activity may be occurring on the ocean floor of Enceladus, similar to the hydrothermal vents on Earth's ocean floors where life thrives in complete darkness, using chemical energy instead of sunlight. The energy that powers Enceladus's activity comes from tidal heating. As Enceladus orbits Saturn, it is stretched and squeezed by Saturn's gravity, and these tidal forces generate heat through friction in the Moon's interior. The effect is enhanced by an orbital resonance with the Moon Dione, which keeps Enceladus's orbit slightly elliptical, maximizing the tidal flexing. Without this resonance, Enceladus might be geologically dead, its ocean frozen solid. Instead, it is one of the most active worlds in the solar system. The surface of Enceladus outside the south polar region is bright white, one of the most reflective surfaces in the solar system. This high reflectivity comes from fresh ice, continually deposited by the fallback of particles from the plumes. The northern hemisphere is heavily cratered, indicating an ancient surface, while the southern hemisphere has fewer craters and shows evidence of recent resurfacing. Fractures, ridges, and smooth plains suggest tectonic activity and cryovolcanic flows have reshaped the terrain geologically recently, perhaps within the last few million years. Mimas, by contrast, appears geologically dead. Its surface is heavily cratered, indicating it has not been resurfaced for billions of years. The giant crater, Herschel, dominates one hemisphere, its central peak rising nearly 6 kilometers above the crater floor. The crater is so large relative to Mimas that the impact which created it must have nearly shattered the Moon. Shock waves from the impact created fractures on the opposite side of Mimas, and the Moon's nearly spherical shape suggests it was able to relax back into equilibrium after the impact. Despite its battered appearance, Mimas plays an important dynamical role in the Saturn system, its gravity creating the Cassini division in the rings. Rhea is the second largest of Saturn's moons and is composed almost entirely of water ice with a small rocky component. Its surface is heavily cratered, but there are 2 distinct types of terrain. One hemisphere is uniformly cratered, while the other has fewer large craters and more small ones, suggesting that some event in Rhea's past caused a difference in the cratering history between the 2 sides. Wispy features, bright streaks that cross the surface, are thought to be fresh ice exposed by tectonic fractures. Rhea has a tenuous atmosphere composed of oxygen and carbon dioxide created by the radiolysis of surface ice, where energetic particles from Saturn's magnetosphere break apart water molecules. Tethys has 2 major features that make it memorable. The first is Odysseus, a massive impact crater 430 kilometers in diameter, more than 2/5 the diameter of Tethys itself. The impact that created Odysseus was powerful enough to have nearly destroyed the Moon, and the crater floor has relaxed over time, rising back toward the level of the surrounding surface due to the slow flow of ice under its own weight. The second major feature is Ithaca Chasma, a vast canyon system that extends for more than 2,000 kilometers, roughly 3/4 of the way around the Moon. The origin of Ithaca Chasma is debated, but it may have formed when a subsurface ocean froze, causing the surface to crack as the interior expanded. Dione is another mid-sized icy moon with a varied surface. Like Tethys, it has wispy terrain, bright features that were once thought to be ice deposits, but are now understood to be bright ice cliffs exposed by tectonic activity. Dione has a higher density than most of Saturn's icy moons, suggesting it has a larger rocky core relative to its ice mantle. Its surface shows evidence of past geological activity, with fractures, ridges, and relatively smooth plains that indicate cryovolcanic resurfacing. Cassini data suggested that Dione, like Enceladus, may have a subsurface ocean, though it appears less active than its smaller neighbour. Iapetus is one of the most visually striking moons in the solar system due to its dramatic two-tone coloration. The leading hemisphere is as dark as asphalt, with an albedo of only about 3 to 4%, while the trailing hemisphere is bright ice with an albedo of 50 to 60%. The dark material, known as Cassini Regio, is thought to be a lag deposit created as ice sublimates from the surface, leaving behind darker, non-ice materials that were mixed with the ice. The source of this dark material may be dust from other moons, particularly Phoebe, which orbits in a retrograde direction and may be slowly losing material that spirals inward towards Saturn and is swept up by Iapetus. The equatorial ridge on Iapetus is equally puzzling. This mountain range is roughly 20 kilometers high and follows the equator almost perfectly, extending for about 3/4 of the moon's circumference. No other moon in the solar system has such a feature. Theories for its origin include the remnants of a collapsed ring system, volcanic activity along an ancient fracture, or material that accumulated when Iapetus was spinning faster in its youth and the moon's rotation slowed due to tidal forces from Saturn. Hyperion is an irregular, potato-shaped moon with a chaotic rotation. Unlike most moons, which are tidally locked to their parent planet, Hyperion tumbles unpredictably as it orbits Saturn. Its surface is covered with deep, sharp-edged craters that give it a sponge-like appearance. The material of Hyperion appears to be very porous, with a low density suggesting it is more than half empty space. This high porosity may explain why impacts create such deep craters, as the impactors punch into the fluffy material rather than excavating solid ice. Phoebe orbits far from Saturn in a retrograde direction, taking more than a year and a half to complete one orbit. Its dark surface is rich in carbon and organic molecules, very different from the bright icy surfaces of Saturn's inner moons. Phoebe is thought to be a captured object from the Kuiper Belt, a region beyond Neptune filled with icy bodies left over from the formation of the solar system. Studying Phoebe gives scientists a sample of material from the outer solar system without needing to send a spacecraft all the way to the Kuiper Belt. A tenuous ring of material orbits Saturn at Phoebe's distance, created by impacts on Phoebe that eject material into space. This Phoebe ring is enormous, extending from at least 4 million to 13 million kilometers from Saturn, but it is so diffuse that it was only discovered through infrared observations. The small inner moons that orbit near the rings are often irregularly shaped and have surfaces dominated by impacts. Janus and Epimetheus share nearly the same orbit, and every 4 years they swap positions in a gravitational dance unique in the solar system. When the inner moon catches up to the outer one, they exchange orbital momentum, causing the inner one to move to the outer orbit, and vice versa. This co-orbital relationship is stable over long timescales and may result from the two moons being fragments of a larger body that broke apart. Pan and Daphnis are small moons that orbit within gaps in Saturn's rings. Pan orbits in the Encke gap in the A ring, and Daphnis orbits in the Keeler gap, also in the A ring. Both moons have accumulated ring material around their equators, giving them a distinctive ridge that makes them look like flying saucers. These equatorial ridges are thought to form from the accretion of particles that collide with the moons at low velocities, sticking to the surface rather than bouncing away. Prometheus and Pandora are shepherd moons that orbit on either side of the narrow F ring. Their gravitational influence constrains the ring particles, preventing the ring from spreading out. The F-ring is dynamic, with kinks, clumps and braids that change over time, driven by the gravitational perturbations of these moons, and possibly by small moonlets embedded within the ring itself. Together, Saturn's moons form a system of incredible diversity, each world shaped by its own history of formation, geological activity, and interaction with Saturn and the other moons. They are natural laboratories for studying planetary processes, from impact cratering to tidal heating, from organic chemistry to the potential for life in subsurface oceans. Each moon adds another piece to the puzzle of how planetary systems form and evolve, and each one invites us to imagine what it would be like to visit these distant, alien landscapes. Standing on the surface of one of these moons, perhaps on the bright ice plains of Dione or among the towering crater walls of Tethys, you would see Saturn hanging in the sky, enormous and serene, its rings stretching across the heavens. Other moons would move across the sky in their orbits, appearing and disappearing behind Saturn or transiting across its face. The stars would shine steadily without twinkling, since there is no atmosphere to distort their light. The sun would be distant and dim, but bright enough to read by, casting long, sharp shadows across the ice. It would be a place of profound stillness and alien beauty, a reminder that our solar system is filled with worlds waiting to be explored, each one unique, each one holding secrets about the nature of planets and moons, and perhaps about the possibilities for life beyond Earth. Beyond the visible splendor of its rings and moons, Saturn possesses invisible structures that shape the space around it and influence everything within its domain. The planet generates a powerful magnetic field, creating a magnetosphere that extends millions of kilometers into space, far beyond the orbits of its innermost moons. Within this magnetosphere, charged particles are trapped and accelerated, creating radiation belts and auroras, driving complex interactions between Saturn's magnetic field, its moons, its rings, and the solar wind. As you continue to rest and let your mind wander through these cosmic phenomena, let us explore the invisible architecture that surrounds Saturn, the magnetic and electric forces that make the Saturn system far more dynamic than visual observation alone might suggest. Saturn's magnetic field is generated deep within the planet's interior, in a region where hydrogen is compressed so intensely that it behaves like a liquid metal. The rapid rotation of Saturn causes this metallic hydrogen to flow in organized patterns, and these flowing electric currents generate a magnetic field through a process known as the dynamo effect. The same process generates Earth's magnetic field, though the materials and scales are vastly different. Saturn's magnetic field is weaker than Jupiter's, but still far stronger than Earth's, extending the planet's influence across millions of kilometers. The axis of Saturn's magnetic field is almost perfectly aligned with the planet's rotation axis, tilted by less than 1 degree. This is unusual among planets with magnetic fields. Earth's magnetic field is tilted by about 11 degrees, and Jupiter's by about 10 degrees. The near-perfect alignment of Saturn's field has puzzled scientists because the dynamo theories that explain planetary magnetic fields typically predict that the field should be tilted relative to the rotation axis. The reason for Saturn's alignment is still not fully understood, and it is one of the outstanding mysteries of planetary magnetism. The magnetosphere is the region of space where Saturn's magnetic field dominates over the solar wind, the stream of charged particles that flows constantly from the sun. The solar wind compresses the magnetosphere on the sunward side, pushing it closer to Saturn, while on the night side, the magnetosphere stretches out into a long tail that extends millions of kilometers downstream from the sun. The boundary between the magnetosphere and the solar wind is called the magnetopause, and it is not a fixed boundary, but rather a dynamic region that moves in and out depending on the strength of the solar wind. Inside the magnetosphere, charged particles are trapped by the magnetic field. Electrons and ions spiral along magnetic field lines, bouncing back and forth between the northern and southern hemispheres. These particles form radiation belts similar to Earth's Van Allen belts. The intensity of radiation varies with distance from Saturn, with the strongest radiation generally found in the inner magnetosphere, close to the planet. However, the rings and inner moons absorb many of these charged particles, creating gaps in the radiation belts at the orbital distances of the moons. The rings of Saturn have a significant effect on the magnetosphere. The countless ice particles that make up the rings are electrically neutral and absorb charged particles from the magnetosphere, creating a relatively clean region close to Saturn. This absorption also creates a current that flows through the ring system, connecting the rings electrically to Saturn's ionosphere. The interaction between the magnetosphere and the rings is complex, with particles and fields influencing each other in ways that are still being studied. Saturn's moons also interact with the magnetosphere in various ways. Enceladus, with its geysers of water vapor and ice particles, acts as a source of material for the magnetosphere. The water molecules released by Enceladus are broken apart by the energetic particles in the magnetosphere, creating a torus of ions that orbits Saturn at Enceladus's distance. This torus contains ions of water, hydrogen, and oxygen, and it contributes to the overall structure of the magnetosphere. Titan, with its thick atmosphere, also interacts with the magnetosphere. As Saturn's magnetic field sweeps past Titan, it creates an induced magnetic field in Titan's ionosphere and generates auroras in Titan's atmosphere. Auroras occur at Saturn's poles, just as they do on Earth, Jupiter, and other planets with magnetic fields and atmospheres. Saturn's auroras are most easily seen in ultraviolet light, where they appear as glowing ovals surrounding each pole. The auroras are created when charged particles from the magnetosphere are funneled along magnetic field lines into the upper atmosphere, where they collide with molecules of hydrogen and create ultraviolet emissions. Saturn's auroras are variable, sometimes flaring brightly and other times fading to dim glows, depending on the activity of the solar wind and the dynamics within the magnetosphere itself. The solar wind carries its own magnetic field, and when this interplanetary magnetic field encounters Saturn's magnetosphere, it can reconnect with Saturn's field, allowing solar wind particles to enter the magnetosphere and energize the auroras. This process, known as magnetic reconnection, is also responsible for geomagnetic storms on Earth and is a universal process that occurs throughout the solar system and beyond. Radio emissions from Saturn were detected by spacecraft long before they arrived at the planet. These emissions, known as Saturn kilometric radiation, are generated by electrons spiraling along magnetic field lines in the magnetosphere. The radio waves are emitted at frequencies of tens to hundreds of kilohertz, below the range that can penetrate Earth's ionosphere and be detected from the ground, but spacecraft in space can detect them easily. The intensity of these radio emissions varies with time and appears to be modulated by the rotation of Saturn, though the exact mechanism is complex because Saturn's magnetic field is so closely aligned with its rotation axis. One mystery that emerged from the Cassini mission is the variable rotation period of Saturn as measured by these radio emissions. Different measurements over the years gave slightly different values for the rotation period, differing by several minutes. This variation is puzzling because the rotation period of the solid interior of Saturn should be constant. The variation in the radio emissions suggests that what is being measured is not the rotation of the solid interior, but rather some feature in the magnetosphere or atmosphere that rotates at a slightly different rate and influences the radio emissions. Determining the true rotation period of Saturn's interior remains an unsolved problem. The magnetosphere also contains a plasma disk, a flattened region of charged particles that is concentrated near Saturn's equatorial plane. This plasma disk is fed by material from Enceladus and other moons and rotates with Saturn's magnetic field. The plasma in the disk is heated by various processes, including collisions and wave-particle interactions, and it emits radiation in the ultraviolet and other wavelengths. Saturn's magnetic field also affects the motion of charged dust particles in the rings and magnetosphere. Small dust grains can become electrically charged by the bombardment of electrons and ions, and once charged, they respond to both the magnetic field and the electric fields in the magnetosphere. This can cause dust particles to move in complex spirals or to be levitated above the ring plane, contributing to the spokes observed in Saturn's B ring. The study of Saturn's magnetosphere has implications for understanding magnetospheres around other planets and even around exoplanets orbiting distant stars. The processes that occur in Saturn's magnetosphere, such as magnetic reconnection, particle acceleration, and plasma dynamics, are universal and occur wherever magnetic fields and charged particles interact. By studying these processes at Saturn, scientists gain insights that apply to astrophysical systems far beyond our solar system. The radiation environment in Saturn's magnetosphere poses challenges for spacecraft. The Cassini spacecraft had to be carefully shielded to survive the radiation it encountered, especially during close passes to Saturn and its inner moons. Despite these challenges, Cassini operated for 13 years, far exceeding its original mission duration, and provided a wealth of data about Saturn's magnetosphere, its dynamics, and its interactions with the moons and rings. As you imagine the invisible forces surrounding Saturn, picture the magnetic field lines arcing through space, connecting the north and south poles, looping around the planet and extending far into space. Charged particles spiral along these lines, glowing with energy in the darkness. The rings cast shadows not only in visible light, but also in the flow of particles, creating dark lanes in the magnetosphere. The moons move through this environment, each one leaving a wake in the plasma, each one contributing material or absorbing energy. The entire system is interconnected, a complex web of forces and matter, all governed by the fundamental laws of electromagnetism and gravity. If you could see magnetic field lines with your eyes, Saturn's magnetosphere would be a structure of incredible beauty, a glowing, dynamic sculpture stretching millions of kilometers, pulsing with the rhythm of the planet's rotation, responding to the gusts and surges of the solar wind, and lit from within by auroras and the glow of energized particles. It is a realm of physics made visible on a planetary scale, a reminder that the universe is filled with invisible structures as real and important as the solid worlds we can see. The story of how humans came to know Saturn is a journey through the history of astronomy itself, from ancient skywatchers who noticed a slow-moving point of light to modern spacecraft that have orbited the planet and revealed its secrets in stunning detail. For thousands of years, Saturn was known only as a wandering star, its true nature hidden by distance and the limitations of the human eye. With the invention of the telescope, Saturn's rings were glimpsed for the first time, though early observers struggled to interpret what they were seeing. Over centuries, better instruments and more sophisticated theories gradually unveiled the reality of this distant giant. As we continue our gentle exploration, let us travel through time and follow the unfolding discovery of Saturn, appreciating how each generation built upon the work of those before. The ancient Babylonians observed Saturn as early as the 7th century BCE, tracking its position among the stars and recognizing it as one of the 5 wandering stars that moved against the background of fixed constellations. They associated it with the god Ninurta, a deity connected with agriculture and war. The ancient Greeks also observed Saturn and named it Phaenon, meaning shining one. Later, the Romans named it Saturnus after their god of agriculture and time, and this is the name that has persisted in Western astronomy. For most of human history, Saturn was simply a point of light, distinguished from stars only by its motion and its steady, non-twinkling appearance. Astrologers gave it significance in their charts, and philosophers speculated about the nature of the planets. But no one could have imagined the rings, the moons, or the complex system we now know exists around Saturn, the planet's slow movement through the zodiac, taking nearly 30 years to complete a circuit, associated it with age, maturity, and patience. Everything changed in 1610 when Galileo Galilei turned his newly built telescope towards Saturn. What he saw confused him. Saturn appeared not as a simple disk like Jupiter, but as a central body with 2 smaller bodies on either side, or perhaps with appendages or handles. Galileo's telescope was not powerful enough to resolve the rings clearly, and he interpreted the structures as moons, or perhaps as parts of Saturn itself. He wrote in a cryptic anagram that Saturn was triplet, with 2 companions that never moved relative to the planet. 2 years later, Galileo looked at Saturn again and was astonished to find that the side structures had disappeared. Saturn now appeared as a simple disk with no appendages. Galileo was baffled and wrote that Saturn had swallowed its children, referencing the myth of the god Saturn devouring his offspring. What Galileo did not realize was that Saturn's rings had turned edge-on as seen from Earth, becoming temporarily invisible. Within a few years, the rings reappeared, and Galileo saw them again before his death, but he never understood what they truly were. It was Christian Huygens, a Dutch astronomer and mathematician, who first correctly identified the structures as a ring system. In 1655, using a more powerful telescope that he had designed himself, Huygens observed Saturn and realized that the planet was surrounded by a thin, flat ring, nowhere touching, and inclined to the ecliptic. He published his findings in a treatise, and also discovered Saturn's largest moon, which he named simply Luna Saturni, though it later became known as Titan. Over the following decades, astronomers continued to study Saturn's rings and discovered that they were not a single solid structure, but appeared to have divisions and variations in brightness. In 1675, Giovanni Cassini discovered a dark gap in the rings, now known as the Cassini division, which separates the A ring from the B ring. Cassini also discovered 4 more moons of Saturn: Iapetus, Rhea, Tethys, and Dione. These discoveries were made possible by improvements in telescope technology and by patient observation over many nights. In 1789, William Herschel, the astronomer who discovered Uranus, discovered 2 more moons of Saturn, Mimas and Enceladus. Herschel also observed what he thought might be additional rings and reported seeing details in the cloud bands of Saturn itself. His son, John Herschel continued the study of Saturn and contributed to the growing understanding of the planet's system. The 19th century brought further refinements in observation and theory. In 1848, American astronomer George Phillips Bond and his father William Cranch Bond discovered a faint inner ring, which became known as the C ring or crepe ring due to its transparent appearance. In 1850, the moon Hyperion was discovered independently by Bond and by William Lassell in England. One of the great theoretical advances came from James Clerk Maxwell, the physicist who formulated the equations of electromagnetism. In 1859, Maxwell mathematically proved that Saturn's rings could not be solid structures, as they would be unstable and tear themselves apart. He demonstrated that the rings must be composed of many small particles, each orbiting Saturn independently. This was a remarkable achievement of theoretical physics, using mathematics to reveal the true nature of an object millions of kilometers away, long before spacecraft could visit and confirm the theory directly. The 20th century brought spectroscopy, a technique that analyzes the light from celestial objects to determine their composition. By studying the light reflected from Saturn and its rings, astronomers determined that the rings were made primarily of water ice. They also began to understand Saturn's atmosphere, identifying hydrogen, helium, methane, and ammonia in the planet's clouds. In the latter half of the 20th century, humanity finally sent emissaries to visit Saturn directly. The first spacecraft to reach Saturn was Pioneer 11, which flew by the planet in September 1979. Pioneer 11 confirmed the presence of Saturn's magnetic field, discovered a new narrow ring called the F ring, and returned the first close-up images of Saturn and its moons. The spacecraft passed within 21,000 kilometers of Saturn's cloud tops, closer than any spacecraft before, and provided valuable data about the planet's radiation environment. The Voyager missions provided the next great leap in our understanding of Saturn. Voyager 1 flew by Saturn in November 1980, followed by Voyager 2 in August 1981. These twin spacecraft carried advanced cameras and instruments and returned stunning images that revealed the intricate structure of Saturn's rings, the complex banding in its atmosphere, and detailed views of several moons. Voyager discovered new moons, observed the geysers of Enceladus, studied Titan's thick atmosphere, and revealed the hexagonal storm at Saturn's north pole. The data returned by the Voyager spacecraft filled libraries and kept scientists busy for years analyzing the wealth of new information. Despite the success of the Voyager missions, many questions remained unanswered. The flybys provided only brief glimpses of Saturn and its moons, lasting hours or days at most. To truly understand Saturn, a spacecraft would need to orbit the planet, observing it through multiple seasons and studying its moons repeatedly over many years. This need led to the development of the Cassini-Huygens mission, a joint project of NASA, the European Space Agency, and the Italian Space Agency. Cassini was launched in 1997 and took nearly 7 years to reach Saturn, arriving in July 2004. The spacecraft entered orbit around Saturn and began a mission that would last 13 years, far exceeding its original planned duration. Cassini carried 12 scientific instruments and the Huygens probe, which was released to land on Titan. The mission was a phenomenal success, revolutionizing our understanding of Saturn, its rings, and its moons. Cassini observed Saturn through half of a Saturnian year, watching the seasons change and the rings and atmosphere respond. It discovered new moons, observed the geysers of Enceladus up close, flew by Titan more than 120 times, mapped the rings in unprecedented detail, and studied Saturn's magnetosphere, auroras, and storms. The spacecraft observed the massive storm that erupted in 2010, watched moonlets shepherd ring particles, measured the age and composition of the rings, and sampled the plume of Enceladus to analyze its chemistry. In September 2017, as Cassini's fuel ran low, the mission team commanded the spacecraft to dive into Saturn's atmosphere, ensuring it would not accidentally crash into and contaminate any of Saturn's potentially habitable moons. Cassini's final plunge provided data about Saturn's atmosphere and magnetic field right up until the spacecraft broke apart and burned up in the planet's atmosphere. It was a fitting end for a mission that had given humanity an intimate portrait of one of the solar system's most beautiful and complex worlds. The study of Saturn continues today using ground-based telescopes, space telescopes like Hubble, and analysis of the data returned by Cassini. Future missions to Saturn are being planned, including the Dragonfly mission to Titan, which will explore that moon's surface and atmosphere in the late 2030s. Each generation of astronomers and planetary scientists builds upon the discoveries of the past, using better tools and deeper understanding to reveal more about Saturn and its place in the cosmic order. As you rest and reflect on this long journey of discovery, consider how the study of Saturn mirrors the growth of human knowledge itself. From naked-eye observations in ancient times to spacecraft orbiting the planet, each step required patience, ingenuity, and the willingness to ask new questions. The story of Saturn is still being written, and future explorers, whether human or robotic, will continue to visit this distant world, uncovering secrets we have not yet imagined and finding answers to questions we have not yet thought to ask. The Cassini spacecraft stands as one of the greatest achievements in the history of space exploration. For 13 years, from 2004 to 2017, Cassini orbited Saturn, studying the planet, its rings and its moons with an intensity and depth unprecedented in planetary science. The mission returned over 450,000 images, discovered new moons and ring structures, sampled the composition of plumes from Enceladus, and delivered the Huygens probe to the surface of Titan. As we near the end of our journey through the wonders of Saturn, let us spend time with Cassini, exploring what this remarkable mission revealed and how it changed our understanding of the Saturn system and the possibilities for life beyond Earth. Cassini was a large and complex spacecraft, about the size of a school bus and weighing nearly 6 tons when fully fueled. It carried 12 scientific instruments, each designed to study different aspects of Saturn and its environment. There were cameras for visible and infrared imaging, a radar to map Titan's surface, spectrometers to analyze the composition of atmospheres and surfaces, a magnetometer to measure magnetic fields, instruments to detect dust and charged particles, and a radio science experiment that used the spacecraft's radio signals to probe the atmospheres and interiors of Saturn and its moons. The journey to Saturn was long and required gravity assists from Venus, Earth, and Jupiter to gain the speed needed to reach the outer solar system. Cassini flew by Venus twice, then passed by Earth and the Moon, and finally swung past Jupiter in late 2000, using the giant planet's gravity to fling it towards Saturn. The Jupiter flyby also provided an opportunity to observe Jupiter and compare it with Saturn, revealing differences and similarities in their atmospheres, magnetic fields, and ring systems. When Cassini arrived at Saturn in July 2004, it performed a critical engine burn to slow down and be captured by Saturn's gravity into orbit. This Saturn orbit insertion burn was one of the most nerve-wracking moments of the mission, as any failure would have sent the spacecraft flying past Saturn, wasting years of work and billions of dollars. The burn was successful, and Cassini became the first spacecraft to orbit Saturn. Shortly after arriving, Cassini released the Huygens probe, a European-built lander designed to descend through Titan's atmosphere and land on the surface. Huygens separated from Cassini on Christmas Day 2004 and coasted toward Titan. On January 14, 2005, Huygens entered Titan's atmosphere and began its descent, taking measurements and images throughout the 2.5-hour fall. Huygens transmitted data back to Cassini, which relayed it to Earth. The probe survived the landing and continued to send data for over an hour from the surface, becoming the most distant landing ever achieved by a spacecraft. The images returned by Huygens showed a world that looked eerily like Earth in some ways. Rounded pebbles of ice littered the landing site, and channels carved by liquid methane stretched into the distance. The sky was a hazy orange, and the lighting was dim, like a heavily overcast day on Earth. The data confirmed that Titan has a methane cycle similar to Earth's water cycle, with liquid hydrocarbons playing the role that water plays on our planet. Cassini's own observations of Titan over the course of the mission revealed even more. The spacecraft used its radar to map Titan's surface through the opaque atmosphere, discovering vast dune fields near the equator, mountain ranges, and the hydrocarbon lakes and seas of the polar regions. Cassini watched the seasons change on Titan, observing clouds forming and dissipating, rainstorms soaking the surface, and the gradual evaporation and refilling of lakes. The spacecraft flew by Titan 127 times, each flyby revealing new details and deepening our understanding of this complex moon. But Titan was not the only moon to receive Cassini's attention. The spacecraft also made close flybys of Enceladus, discovering the geysers erupting from the South Polar region during a close pass in 2005. This discovery was unexpected, as Enceladus had been thought to be a small, frozen, geologically dead world. The geysers indicated internal heat and liquid water, and subsequent flybys allowed Cassini to fly through the plumes and analyze their composition. The detection of salt and organic molecules in the plumes suggested that Enceladus has a subsurface ocean in contact with a rocky core, making it one of the best places in the solar system to search for extraterrestrial life. Cassini also observed other moons in detail. It studied the two-toned surface of Iapetus, mapped the heavily cratered terrains of Rhea and Dione, observed the strange equatorial ridge on Iapetus, watched the shepherd moons Prometheus and Pandora interact with the F-ring, and discovered new small moons embedded in the rings. Each moon told a story about the history and evolution of the Saturn system. The rings received intense scrutiny from Cassini. The spacecraft observed the rings from every angle, in different wavelengths of light, and at different times as the rings changed their appearance with the seasons. Cassini discovered propeller-shaped structures in the rings created by embedded moonlets, observed the spokes in the B-ring, studied the braided structure of the F-ring, and measured the composition and size distribution of ring particles. The mission also observed occultations, events where stars or the sun passed behind the rings as seen from Cassini, allowing scientists to probe the structure and transparency of the rings at high resolution. One of the most dramatic events observed by Cassini was a giant storm that erupted in Saturn's northern hemisphere in late 2010. The storm grew rapidly, spreading eastward around the planet, and eventually encircling Saturn entirely in a bright white band. Amateur astronomers on Earth also observed the storm, and their observations complemented Cassini's data. The storm lasted for months and provided a unique opportunity to study convection and dynamics in Saturn's atmosphere. Cassini also observed Saturn's auroras, the hexagonal storm at the North Pole, and seasonal changes in the atmosphere. The spacecraft watched as the shadow of the rings moved across the planet during the equinox, creating a rare opportunity to observe ring structures illuminated from behind by the sun. These backlit views revealed details invisible at other times and led to the discovery of previously unknown rings and moonlets. As the mission progressed, Cassini performed increasingly daring orbits. In its final year, the spacecraft executed the grand finale, a series of 22 orbits that took it between Saturn's innermost rings and the planet's atmosphere. These orbits provided the closest ever views of Saturn and allowed measurements of the planet's gravitational and magnetic fields with unprecedented precision. The data from the grand finale helped determine the mass of the rings, the rotation rate of Saturn's interior, and the structure of the planet's magnetic field close to the planet. On September 15, 2017, Cassini made its final plunge into Saturn's atmosphere. The spacecraft sent back data as it descended, measuring the composition and temperature of the upper atmosphere until the signal was lost as Cassini broke apart and vaporized in the heat and pressure. The end of the mission was emotional for the team of scientists and engineers who had worked on Cassini for decades, but it was also a triumphant conclusion to one of the most successful missions in the history of space exploration. The legacy of Cassini is immense. The mission returned a wealth of data that scientists are still analyzing, leading to discoveries years after the mission ended. Cassini's observations of Enceladus have made that moon a prime target for future missions searching for life. The detailed study of Titan has transformed our understanding of that moon and has led to the selection of Dragonfly, a mission that will send a rotorcraft to explore Titan's surface. The measurements of Saturn's rings have revealed their youth and dynamic nature, challenging previous assumptions about their age and origin. Cassini also inspired a generation of scientists, engineers, and the public. The stunning images of Saturn and its moons captured the imagination of people around the world, reminding us of the beauty and wonder of the universe. The mission demonstrated what can be achieved when nations and institutions collaborate on a common goal, pooling resources and expertise to explore the unknown. As you imagine Cassini orbiting Saturn, think of the spacecraft as a traveler from Earth, a representative of humanity venturing into the far reaches of the solar system. For 13 years, Cassini was our eyes and ears at Saturn, sending back messages from a world more than 1 billion kilometers away, revealing sights no human had ever seen. The spacecraft witnessed sunrises over Titan's hazy horizon, watched Enceladus's geysers erupting against the backdrop of space, saw the rings shimmer in the distant sunlight, and felt the tug of Saturn's gravity holding it in a cosmic embrace. Cassini's journey ended in flame and silence, but its discoveries will echo through the ages, a testament to human curiosity and the desire to explore beyond the boundaries of our world. As our journey through the wonders of Saturn draws to a close, let us step back and appreciate Saturn's place in the larger cosmic context. This magnificent planet is not an isolated object, but a part of the intricate dance of worlds that make up our solar system, shaped by the same processes that formed Earth and the other planets, connected to the Sun by invisible threads of gravity and light, and offering insights into the nature of planetary systems around other stars. In these final moments of reflection, as you continue to rest and let your mind wander gently through the cosmos, we will consider what Saturn teaches us about the universe, about the forces that govern celestial bodies, and about our own small but meaningful place in the vastness of space. Saturn formed from the same primordial cloud of gas and dust that gave birth to the Sun and the entire solar system approximately 4.5 billion years ago. In the cold outer reaches of the solar nebula, beyond the frost line where water could condense into ice, solid materials were abundant enough to build the cores of giant planets. Saturn's core grew from the accumulation of ice and rock until it became massive enough to gravitationally attract the surrounding hydrogen and helium gas. The process of gas accretion was rapid once it began, and Saturn swelled to its current size within a few million years, a brief moment in cosmic time. The position of Saturn in the solar system, roughly 9.5 times farther from the Sun than Earth, places it in a region where temperatures are cold and sunlight is weak. At Saturn's distance, the Sun appears about 100 times dimmer than it does from Earth, providing only about 1% of the solar energy per unit area. This distance has shaped every aspect of Saturn, from the composition of its atmosphere to the chemistry of its moons and the dynamics of its rings. The cold temperatures allow methane to exist as a gas on Titan and as a liquid on its surface, creating a world unlike any in the inner solar system. Saturn's gravity governs the motion of everything in its vicinity. The rings orbit Saturn because of gravity, each particle following an elliptical path determined by its velocity and distance from the planet. The moons orbit Saturn for the same reason, their paths precisely dictated by the balance between their orbital velocity and Saturn's gravitational pull. The complex interactions among the moons, creating resonances and tidal heating, are all manifestations of gravity acting across distances. Even the shape of Saturn itself, bulging at the equator due to its rapid rotation, is a result of the interplay between gravity pulling inward and centrifugal effects pushing outward. Gravity also connects Saturn to the other planets in the solar system. The gravitational influence of Jupiter, the largest planet, affects Saturn's orbit, creating small perturbations that change over time. These interactions between the giant planets have shaped the architecture of the solar system, influencing where asteroids and comets orbit, and occasionally sending objects into the inner solar system, where they can collide with terrestrial planets. The gravitational relationship between Jupiter and Saturn has even been implicated in models of solar system formation that suggest the giant planets migrated from different orbits in the early solar system, reshaping the distribution of material and perhaps triggering the late heavy bombardment that scarred the surfaces of the Moon and inner planets. Saturn, like all planets, is a product of the laws of physics. The same equations that describe the motion of a ball thrown on Earth also describe the orbit of Saturn around the Sun. The same thermodynamics that governs heat engines on Earth explains why Saturn radiates more heat than it receives from the Sun. The same fluid dynamics that creates weather patterns in Earth's atmosphere creates the bands, storms, and hexagonal vortex on Saturn. Studying Saturn allows scientists to test physical theories in extreme conditions, where pressures, temperatures, and scales are vastly different from those accessible in laboratories on Earth. The existence of Saturn's rings challenges us to understand the dynamics of countless individual particles interacting gravitationally and through collisions. The mathematics that describes the rings is related to the mathematics used to study galaxy formation, where billions of stars interact gravitationally to create spiral arms and other structures. The study of ring dynamics has applications in astrophysics, helping us understand protoplanetary disks around young stars where planets are forming, and accretion disks around black holes where matter spirals inward under extreme gravitational forces. Saturn's moons, particularly Enceladus and Titan, have become central to the field of astrobiology. The discovery of liquid water beneath Enceladus's ice and the complex organic chemistry on Titan's surface raise the possibility that life could exist in forms and environments very different from Earth. If life can arise in the cold, dark subsurface oceans of an icy moon, or in the methane lakes of Titan, then the potential habitats for life in the universe expand enormously. Most planets and moons in the universe do not resemble Earth, but many may have subsurface oceans or exotic surface chemistry. Studying Saturn's moons helps us understand what to look for when searching for life beyond our solar system. The study of Saturn also has implications for understanding exoplanets, planets orbiting other stars. Gas giants are common in other solar systems, and many have been discovered through transit and radial velocity methods. Some of these exoplanets are hot Jupiters, giant planets orbiting very close to their stars, while others orbit at distances more similar to Jupiter and Saturn in our own system. By understanding how Saturn's atmosphere, magnetosphere, and ring system work, scientists can make predictions about what exoplanets might be like and what features might be detectable through telescopes. Saturn reminds us of the diversity of worlds in the universe. Each planet and moon is unique, shaped by its own history of formation, geological activity, and environmental conditions. Saturn's rings are unlike anything else in the solar system in their size and complexity. Titan's methane cycle is unique among moons. Enceladus's geysers and subsurface ocean make it a standout among small, icy moons. This diversity tells us that the universe is filled with surprises, that nature is more creative than our imaginations, and that every new world we explore will offer something unexpected. Looking at Saturn also puts our own existence into perspective. The Earth, for all its beauty and complexity, is just one small world among countless others. The processes that shape Earth, plate tectonics, weather, the water cycle, are variations on physical principles that operate throughout the universe. We are not separate from the cosmos, but a part of it, made of atoms forged in stars, living on a planet shaped by the same forces that shape all worlds, looking out with curiosity at the universe that gave us birth. Saturn has been a companion to Earth throughout human history, visible in our skies, a steady point of golden light moving slowly through the constellations. Ancient peoples watched it and wondered. Galileo glimpsed its rings and was puzzled. Huygens understood them and marvelled. Maxwell proved mathematically what they must be. Voyager and Cassini flew there and showed us the reality. Each generation has brought us closer to understanding this distant world, and each discovery has deepened our sense of wonder. As you lie in the gentle darkness, letting these thoughts settle into your mind like snowflakes falling softly on a winter night, consider the fact that Saturn is real. It exists right now, orbiting the sun, its rings glittering in the faint sunlight, its moons drifting through the cold vacuum of space. Titan's rivers are flowing, Enceladus's geysers are erupting, the hexagonal storm is spinning at the North Pole. All of this is happening at this very moment, more than 1 billion kilometers away, in the silent vastness of space. And we, through the power of science and exploration, have come to know it, to understand it, to see its beauty and complexity. The 100 facts about Saturn that we have woven through this journey are not just pieces of information to be memorized. They are windows into the nature of reality, invitations to think deeply about how planets form, how atmospheres work, how gravity shapes moons and rings, how life might arise in unexpected places, and how human curiosity drives us to explore beyond the familiar. Each fact connects to others, forming a web of understanding that encompasses physics, chemistry, geology, astronomy, and even philosophy. Saturn, in all its golden glory, reminds us that the universe is vast and beautiful, that there are worlds beyond our world, that exploration is a journey without end. It challenges us to keep looking up, to keep asking questions, to keep sending our spacecraft farther and deeper into the cosmos. And perhaps most importantly, it reminds us that we are capable of understanding the universe, that the human mind can reach across billions of kilometers and comprehend the nature of distant worlds, that we are part of something larger than ourselves. As you drift towards sleep, let the image of Saturn fill your thoughts. See the rings arcing gracefully across the blackness, the butterscotch clouds swirling in endless bands, the moons circling in their ancient orbits. Imagine standing on Titan's surface, gazing up at a sky filled with orange haze and a distant, dim sun. Imagine floating among the ice particles of the rings, each one a tiny world reflecting light in every direction. Imagine the quiet majesty of a planet that has orbited the sun for billions of years, witnessing the history of the solar system, unchanged and unchanging, a monument to the grandeur of nature. The journey through Saturn's wonders has been long, but it has also been a gift a chance to travel in your mind to a place few humans will ever visit physically, to see through the eyes of spacecraft and the minds of scientists, to touch, if only in imagination, the reality of another world. And as you close your eyes and let sleep carry you away, know that Saturn will still be there tomorrow, and the day after, and for billions of days to come, spinning silently in the darkness, waiting for the next explorer, the next question, the next moment of discovery. The universe is patient. It has all the time in the world. And so, in our own small way, do we.